So actually, I am Naoto Nagaosa from Riken in Japan. And today I will talk about the magnetic oxides. So let me start by thanking the organizers, especially Vincent for organizing this and inviting me to this very nice summer school. And then also many of his colleagues. So thank you very much. And then let me start by mentioning some article by Daniel Komsky, who passed away last August, unfortunately. But he has a preprint on this archive, exactly the same title of magnetic oxides. So that's why I read his article, and this is a sort of a summary of his article. So he listed up important issues related to the magnetic oxides, spin orbit, and intradionic Hund's exchange, crystal field splitting, and Jahn-Teller effect, etc. And the intercycle effect, electron tunneling between ions, namely the transfer integral, and the strongly correlated system, Fermi surface, etc. And also exchange coupling. Could be a nice topic, different between different spin components. And this one will be quite important, and I will touch on this. And there are insulating magnetic oxides where the magnetoelectric and multi-ferric behavior is observed, and the various transitions, including structure and the metal insulator transitions. And lastly, he mentioned about applications. So please visit these articles if you are interested in. And accordingly, I made a plan for this lecture. So isolated ions, interside effect, and exchange interactions, frustrated magnetism, various ordering and metal insulator transition, spin orbit interaction and the non-collinear magnetism, and lastly, superconductivity. So because this is such a broad field, it is impossible to cover all the issues in the magnetic oxide, but let me try to summarize this field from my viewpoint. Okay, so let me start by isolating magnetic ions, right? So if we have magnetic ions, you have a 5-fold degenerate d orbitals. Namely, I will mention about the 3D materials for most of my talk. And then under the influence of anion, right, surrounding the transition metal ion. For example, if you have a OH symmetry, so this corresponds to the configuration where this magnetic ion is surrounded by, for example, the oxygen atoms, plus minus Z, X, Y, minus Z, and Y, and minus Z, 6 oxygens, right? So that is the MO6 configuration showing the octahedron, right? So this is a irreducible representation of a point group symmetry of that cluster. So then there are 2-fold EG orbital and 3-fold T2G orbitals. So neglecting the spin degrees of freedom, just the orbital, right? So this is a cartoon for the wave function, right? So for this T2G orbital, X, Y, Y, Z, and ZX, right? So most of the wave function is pointing somehow away from this oxygen. So oxygen is usually -2, so then it will be repulsive for the electrons living on this magnetic ion, right? So that's why once you have EG orbitals, which is mostly pointing towards this oxygen, then it will have a repulsive interaction. So that's why the energy is shifted up, right, compared with this T2G 3-fold degenerate, right? So if you lower the symmetry furthermore, for example, C4V or D4H, then these orbitals are further split into these levels, right? So these 2 lines means 2-fold degenerate. And actually, if you have this kind of degeneracy of the orbital, right? So then if you lower the symmetry, then you have linearly splitting. So if you do the perturbation theory for the degenerate state, then your off-diagonal matrix element leads to the energy splitting, which is a linear with respect to the distortion. But usually the energy cost to the distortion is distortion square. So distortion square is always defeated by the linear term with respect to the energy gain, right? So for example, if you have only one electron in this EG orbitals, then this one electron is occupying this once you have this symmetry lowering distortion. So then this is so-called Yann-Teller instability. So the degeneracy always gives rise to some instability towards a distortion to a lower symmetry. So that is the Yann-Teller effect. Okay, so what I summed up is the orbital under the influence of ligand potential, and because you have an overlap of a wave function between the d orbitals and the p orbitals of oxygen. So usually you have a hybridization in addition to this Coulombic interaction. So these two effects give rise to this so-called splitting 10dq. And this is the most fundamental quantity which determine the electric states of manganese oxides, or magnetic oxide, right? And degeneracy lifted depending on the symmetry, and the Yann-Teller effect to lift the degeneracy by the atomic displacements. So this is a summary of this slide. Okay, so now let's go to the Coulombic interaction. Previously, I just mentioned about the single particle levels, but now we want to worry about the Coulombic interaction. So in short, I think a Coulomb repulsion prefers rotation, so which is Hund's rule. So there are three rules. So the number one is you should maximize the spin S for the ground state of electric wave function. So this is coming from the combination of Pauli exclusion and the Coulombic interaction, right? So the Pauli exclusion says that if you have, let's say, parallel spin, then you cannot occupy the same spatial position, right? So that's why the Coulombic interaction is reduced once you have a parallel spin. So if you have a parallel spin for all the electrons in the atom, then you should have a lowest energy. So that is rule number one. So this one is given by this Hamiltonian, Hund's coupling JH, and this alpha and beta correspond to the different orbitals of atom, same atom. And then I is a spin component, X, Y, Z. So this is a Heisenberg type, okay? But within this maximal spin S degeneracy, then still you could have an orbital angular momentum L. And you should maximize this L also within the constraint of maximum spin S, right? So this is a second law. So usually in the textbook, it is not well explained, but my understanding is the following, right? If you have a track in the stadium, and then the runners are running in the same direction, right? Clockwise or counterclockwise in any way. So then you don't have collisions when rotating in the same direction. So imagine that each runner is running in the random way, clockwise and counterclockwise. Then you have many, many collisions, right? So collision, namely the this access of each other, means you will lose the Coulombic energy. You will cost your Coulombic energy. So that's why the lower energy Coulombic energy state should be the maximum orbital angular momentum L. And the third rule, last one, is related to the spin-orbit interaction. So within the single atom, you should have L dot S coupling, right? And this lambda, the strength of the spin-orbit coupling is proportional to the atomic number G square. So this is typically 20 to 70 milli-electron volt for the 3D atoms. But if we go to the 4D or 5D, increasing the atomic number, then this energy should be very large, typically of the order of 0.4 or 0.5 electron volts. This is actually the comparable to the Coulombic energy for the 4D electron system. And then J should be the absolute value of S minus L when the number of electrons is less than half. For the 3D case, it is 5. less than 5. And if this n is larger than 5, half, then it should be the S plus L. So this is coming from the spin-orbit interaction. So these are the 3 rules of Wundt's. Okay, so now we introduce 2 concepts. So one is 10dq, and the other is Wundt's rule. So there is a competition between these 2 couplings, right? So once your Wundt's rule is dominating, Coulombic interaction is large, then you should maximize your spin. So suppose you have 5 electrons in the d orbitals split into the EG and T2G orbitals. Then you need to occupy the 5 orbitals singly, in a single way, right? So then the total spin becomes 5 halves, right? But once your 10dq is large enough, right, then you should occupy the lower T2G orbitals. And then you fill the electron in this way. So you cancel the 2 of spin 1 half, and eventually you have only 1 half. So spin 1 half state becomes a ground state. So this occurs for the 4D and 5D orbitals, and sometimes for the 3D. So this is one typical example of this composition, namely the cobalt oxides. For example, if you have a D6 configuration, right? So then S could be 3 possible values. Spin 0 is a low spin state, and the intermediate spin state you have a 1, and the high spin state is 2. So which is schematically shown in the left of these figures in this way. So then this shows some magnetic transition. And X is a doping concentration, so we are interested in this X0 curve. So it is a typical insulating behavior towards very high resistive states at lower temperature. But then magnetically, this is a magnetic susceptibility, so then it shows some. This is impurity contribution, I believe, and then you have a magnetic gap, which is typically the 230 Kelvin. Okay, so this is a calculation and the experimental result for the intermediate spin state realized in this lanthanum cobalt oxides. By the way, in any time you can interrupt me and raise questions. Is that okay? Okay? Okay. So now let me proceed to the intersite effect, right? So up to now, actually, basically, I consider this single atom properties. Yeah, I didn't introduce so the orbital energy difference, but let me go back to the simplest case where you have this Coulombic interaction, right, between the same orbital, electrons in the same orbital, right? So this is the simplest case, right? So single orbital Hubbard model. But in addition to that, so we have an intersite effect, which comes from the hopping or tunneling between the different ions, I site and J site, right? So then we have a competition between the T term and the U term, which is described by this Hubbard model, the hopping and the Coulombic interaction. So if you fix your T, right, transfer integral, then increase your U. So the W is so-called bandwidth. G is number of nearest neighbors. Okay. So then if you increase your U, then this shows density of states for the single particle Green's function. And starting from the 0 U, so you have a metal. Let's think about the half filling case. Namely, only half of the electron is occupying, right? So then, in this case, you have a well-defined film surface, and you have a metal, right? And then, if you increase U, then you have still the metal, but at some critical value of U critical, then this opens the gap for the electron density, density of states. Okay, so then this corresponds to the metal to insulator transition Many people call it MIT, right? Or MOT transition. So here is a theoretical treatment of this MOT transition as you increase your U. So this density of states correspond to the imaginary part of a single particle Green's function develops in the following way. First, you have a metallic density of states, and then there appears some splitting of a peak, which correspond to eventually the upper Hubbard band and the lower Hubbard band, and then this so-called Fermi liquid state, right? So at the Fermi energy. And eventually, this separation between the Fermi liquid metallic state and this insulating MOT states well and well separated. And eventually, you have a very narrow metallic heavy fermionic behavior, and eventually becomes gapped. So this central peak corresponds to the Fermi liquid disappears at some critical point you see. So this is an evolution of density of state for the single electrons. So then in this MOT insulating state, right? So you occupy one of the spin up or spin down state. So in this state, you have a huge degeneracy of the ground state at this level because you have a spin degrees of freedom. So then you need some additional spin Hamiltonian describing the spin systems to describe the low energy states of this MOT insulator. So that is a story for the single orbital case. But now we have a more complication because the theme of this lecture is magnetic oxides. So where is oxides, right? So then oxide means you have 2p orbitals, right? Here we have 2p, 2p orbitals here, right? So usually you have 2p orbitals well below this 3D. But now this 2p orbital is doubly occupied, so it becomes inert. So namely, this is a 2 minus ionic configuration. And then you have a singly occupied d orbitals, right? And at the MOT transition, this density of state will split into the lower Hubbard one and the upper Hubbard one. So this is the usual picture described by this Hubbard Hamiltonian I just mentioned. But once you have these p orbitals, namely the oxygen 2p states, then sometimes this 2p state becomes much higher in energy and approaching to the Fermi energy. So in that case, here is a MOT gap between the lower Hubbard band and upper Hubbard band. But in between, you have this oxygen 2p orbitals, right? So these two cases are well separated. One is a MOT-Hubbard insulator, and the other is a charge transfer insulator, right? And then in the figure, in the plane of delta, charge transfer energy and the Coulombic interaction T, normalized by the basically the bandwidths, right? So you can distribute the various materials in this diagram. And if the U is large enough, then, when delta is large enough, delta is basically this energy. So that's why near the Fermi energy, your state can be described by the Hubbard model only. So this is called the MOT-Hubbard insulator, vanadium, titanium, chromium. So this kind of MOT insulator correspond to this regime. And then once your U is big enough and your charge transfer energy is smaller, then you have this electric configuration. And this listed material shows this behavior, and we call it charge transfer insulator. And we have a crossover between the two cases. Okay, so if you look at the magnetic oxide, so first you should look at which position of your materials sitting in this phase diagram. Okay, so now this is a more concrete example for the sodium, some metallic ion, and O2. And depending on the magnetic ion, titanium, vanadium, cobalt, chromium, etc. I'm sorry that this X and Y axis are reversed between this one and this one. But now in this case, you can separate or classify your materials into the mode type and charge transfer type. So this is one example where this classification scheme works. Okay, but now we are recently interested in the charge transfer insulator because these are cuprates and nickelates, which is the most exciting materials for us, belongs to the charge transfer insulator, where the oxygen atom play an important role. Suppose, we are starting from this density of state, upper Hubbard band, and the lower Hubbard band, and the charge transfer band, right? So this is a starting point for the mother compounds nearly the molten insulator. But suppose, right, you introduce a hole, doped hole into the kappa, but this hole will enter the oxygen usually, because this is a charge transfer insulator, right? So then your oxygen orbital gains some spins. But this spin is coupled to the D9 configuration of kappa site, and then this will form a singlet. So we call it the Zahn-Rice singlet, and this Zahn-Rice singlet bound state appears between this charge transfer band and upper Hubbard. So these people believe is relevant to the high TC cuprates, superconductivity. And then this state can be described by the so-called TJ model, first proposed by Phil Anderson. So this is a long history about this. But in any case, this Zahn-Rice singlet is one of the key concepts in the magnetic oxides, doped case, okay? And now let me proceed to the exchange interactions, right? And then once you have two sites, I and J site, and then we think about the virtual process, second order perturbation process, which correspond to the hopping from here to here, right? So then you are back to the original molten insulating state. Because once you introduce double occupancy, the energy is much higher. Then it is outside of our low energy sector, right? So then we want to have this energy gain due to the second order process, right? T-square process. But it is possible only when these two spins are antiparallel with each other. We call this kinetic or super exchange interaction. And then usually if you have a molten insulator, then if you have a transfer integral between the two, so your magnetic interaction becomes anti-ferromagnet. But for example, if you have charge carriers or doping hole or electrons, then what happened? Okay, so then so this laser pointer is losing energy. I'm afraid. Is there any pointer? Battery. Thank you. Thank you very much. Okay, this is much better. So then, suppose you have some itinerant conduction electrons coupled to the local spin, right? And due to the strong Hund's coupling, so these two spins are forced to be aligned in the parallel way, okay? So then, once you have alternating anti-ferromagnetic interaction for the local spin, right? And then this hopping is blocked, right? Because now this conduction electron spin is supposed to point down. So it costs a high energy. So that's why for this moving conduction electrons, so the low line, these T2G spins are preferred to be ferromagnetic. So then once you dope, right? Originally you have an anti-ferromagnetic interaction, but you have a doped carriers. So then ferromagnetic interaction is preferred. So there should occur the competition between the two cases, right? And once you have a metallic conduction electrons and a localized spin, this is a different picture from this side. But now in this case, this localized spin will polarize the conduction electrons in the spin. So then this will oscillate with a 2kF periodicity. So then you have anti-ferromagnetic and the ferromagnetic and oscillating as a function of the distance between the two magnetic ions. So this is so-called RKKY interaction, which is typically most relevant to the magnetic semiconductors, right? Like mangan-doped gallium arsenide. And another interesting or important topic is the Kondo problem. Once you have this localized spin due to impurity, for example, and then you have a so-called anti-ferromagnetic interaction between the magnetic and the conduction electron spins. And then this will eventually form a singlet. But this formation of the singlet can be described by the very interesting field theoretical language, such as renormalization group, etc. And then this Kondo singlet is very relevant to the non-abelian field theory, etc. Because this is so-called asymptotic freedom, and which is unique to the non-abelian gauge field theory. So, but this singlet formation and this magnetic ordering due to the RKKY interaction. So these are single spin, but in actual systems, you have a dilute distribution of magnetic impurities. So that's why this interaction and this Kondo effect usually competes. So this is a competition, namely the singlet formation versus the magnetic ordering, which occurs in the heavy ferromagnetic system. That is another most important topics in the strongly correlated electronic systems. Okay. Okay, now back to the rather insulating systems, right? So then there is a famous Goodenough-Kanamori rule to have a sign of the exchange coupling. So basically, you have two mechanisms for the exchange process. First, I mentioned about the Hund's rule for the single atom. But even for the nearest neighbor atoms, different atoms, so this Coulombic exchange energy between the two orbitals becomes ferromagnetic when these two orbitals are orthogonal to each other. So this is a mathematically exact statement. So that direct Coulomb exchange interaction all leads to the ferromagnetic interaction for orthogonal orbitals, right? But once you have overlap or transfer integral, then this leads to the kinetic exchange anti-ferromagnetic interaction. So these are ferromagnetic versus anti-ferromagnetic. This competition determines the sign of exchange coupling between the different atoms. So I'm sorry to put the Japanese Chinese character, but because this is Kanamori. So Kanamori sensei wrote a book about the magnetism, and I put these figures from his textbook explaining the Goodenough-Kanamori rule, right? So then once you have this parallel 180 alignment, this is d orbital, and this is oxygen, right? So then you have a different paths, many paths about exchange coupling. But here you can see that these gx orbitals and 3g square minus r square orbitals, this could be coupled through these p orbitals, right? But this circle means it's active, and this cross means it is forbidden. So then in this case, right, so this exchange process becomes, I think it becomes ferromagnetic, right? So because these two are different orbitals, so that's why we are talking about right. So different orbitals. But once you have homogeneous magnetic ions, so then the exchange coupling becomes antiferromagnetic. But once you have a 90-degree coupling, right? So then the tendency is almost reversed. And once you have a homogeneous magnetic ions, you have a ferromagnetic interaction. And for the similar different atoms, it becomes antiferromagnetic. So because the way that this coupling through these oxygen orbitals are different between the 180 and 90 degree. So that is the idea. Okay, so this rule empirically explain all the many cases which is listed here. I put these tables from this textbook. But once you consider the spin-orbit interaction, the exchange coupling becomes even more interesting, right? So the most famous one is so-called the Jelsin-Sikomoria interaction, which is anti-symmetric between the spin I and the spin J. So this comes from some spin-orbit interaction between the spin I side and J side, and then these two spins tends to be tilted from the parallel or anti-parallel configuration, right? Because of this interaction. So this rotation of the spin is usually a perpendicular to the d vector, which is defined for the bond of these two atomic orbitals, right? But this ij becomes 0 once you have an inversion symmetry at the center of the bond. So the symmetry of the bond is quite crucial to have a Jelsin-Sikomoria interaction. And another even more interesting is this Ising type, so-called compass model, and recently relevant to the Kitaev spin liquid in these materials. Well, this one was proposed by Jacques-Éric several years back. And then in this case, the role of the spin-orbit interaction is crucial. Then this system shows the effective total spin 1/2 state. But because the spin orbit is rather large, then this is different from conventional 3D orbitals case. So then the wave function becomes some linear combination of the complex orbitals, right? So then once you have this complex orbital and consider the exchange path through the this anion, and then some exchange paths are cancelled out. So this interference between the different paths of the exchange coupling leads to the Ising type interaction, which depends on the direction of the bond, right? So this is quite similar to the Kitaev Hamiltonian for the honeycomb lattice. So that's why people are now excited about this possible Kitaev liquid in the two-dimensional honeycomb lattice. And there is some candidate materials. But here is an explanation of the Kitaev model. So you have XX, YY, ZZ Ising type interaction for different direction of the bond. But once you have this Kitaev Hamiltonian, surprisingly, its spin operator can be decomposed into the Majorana fermions in this way, right? So then if we write down this Hamiltonian into this Kitaev or Majorana expression, then it becomes free Majorana fermions. So you can talk about the dispersion of Majorana fermion, and then this exact solution have lots of interesting properties, such as gap opening along under the magnetic field, and you have chiral Majorana fermions. So once you have, these are real materials, so-called alpha ruthenium chloride, not oxides, I'm sorry, but these are very fashionable materials now. And unfortunately, under zero magnetic field, this becomes an anti-ferromagnetic insulator. But under the magnetic field, there occurs some states where no magnetic ordering is observed, right? So these people believe, many of the people believe that this corresponds to the Majorana fermion gapped state. And then you have a chiral majorana channels, which leads to the half of quantum value of kappa xy. So this is an experiment for the thermal Hall effect. And then there is a lot of controversy about this because many people try to reproduce this, but only one group in the world is succeeded this. But many other groups shows rather similar, but not this plateau. So that's why people are now arguing, but still unsettled, right? But in any case, very exciting topics in this exotic spin liquid state. So the other exotic state is observed in the pyrochlor oxide. So the pyrochlor is a crystal structure made from the honeycomb lattice and the triangular lattice stacked around the 1-1-1 direction. And this structure shows a lot of frustration. And here is some list of materials. But our main interest here is Ising spin, or spin ice, right? So the idea is the following. So you have a tetrahedron, right? And on each corner of the tetrahedron, so you have a spin. And instead of hydrogen, right? So this is usual ice, right? But instead of hydrogen position, so we have a spin direction. And in these materials, we have a very strong single spin anisotropy of a spin. And this spin acts as an Ising spin. And then this Ising ice rule contains a lot of huge degeneracy in the classical ground state configuration. And then this is a typical model of ice due to the spin degrees of freedom. And actually, this dysprosium titanium oxide, so 3 plus, correspond to the 9 F orbitals, right? And the titanium is a completely closed shell. So that's why this dysprosium atom acts as an Ising spin ice. And the excitation of this Ising spin can be described by the monopole and the anti-monopole configuration. So this monopole, the meaning of the monopole is that divergence M is a non-zero, plus or minus, and correspond to the monopole and anti-monopole. So this way of describing this excited state works quite well for this Ising spin ice system. And now let's go to the various ordering. I'm running time, and then let me proceed in an effective way. So, and then in that case, the important concept is entanglement or coupling between the spin degrees of freedom and the orbital degrees of freedom. So once you are interested in these EG orbitals, so this corresponds to the almost spin on half. We have a Schutz spin. And then this T spin and S spin, real spin, are coupled in this way. So this is called a Kugel-Komsky model, and considered as fundamental models of magnetic and orbital ordering of magnetic oxides. And you should look at these articles for more details. And this is one example for the thin film plate of manganese oxide. And in this case, we are doping the carriers, right? We are doping carriers. X is the doping concentration. And X versus C over A, this is a strain, right? So this shows the different types of magnetic and orbital ordering. So now this kind of magnetic and orbital ordering can be controlled by the thin film, strain, and also the doping concentration. And for the bulk materials, so this is a typical phase diagram, doping strontium, right? And then temperature and the X phase diagram shows a variety of the phase. So the C is most typical. C-type means the usual antiferromagnetic three-dimensional structure. And the A-type means a rare type, right? So this is up and down for each of the two-dimensional layers and etc. So the spin structure and also the orbital structure entangled. And we try to figure out this phase diagram in terms of rather simple-minded Hubbard model, including the orbital degrees of freedom and also the Hund's coupling between the T2G electrons and conduction electron, etc. But the important thing is this itinerancy of a conduction electron is essential to describe all this complicated phase diagram. So in the metallic systems, so the situation is much more rich or complex. Go ahead.
May I ask a question?
Yes.
In your previous slide,
Oh.
if you have a C-type antiferromagnetic order,
Yeah.
Ci is the same, or what does it mean, this I?
I is an insulator. Sorry.
Insulator.
Yeah, C is an insulator. So this is also the insulator. Sorry. Okay, so, but except, in my previous phase diagram, I missed charge ordering state. So the real charge ordering state is alternating this pattern of orbital and also the occupancy of EG electrons. So this 3 plus means we have 1 EG electrons, but 4 plus means, if we look at this configuration, 4 plus means we have only the T2G spins here, right? There is no EG electrons. So these are alternating spin, right? So this chain structure in the diagonal 1-1 direction is accompanied by the charge ordering. So this type of charge ordering and orbital ordering and also the spin ordering. So all happen together. So this leads to the very strong insulating state, right? So then this insulator metal transition can be driven by the temperature and other methods. Okay. Yeah, let me skip this one. Sorry. Okay. こっちだ. And then this metal insulator transition is related to this charge ordering and sometimes Motton ordering, Motton transition. And typically it is driven by the pressure and temperature. But it could be also driven by the magnetic field, just I mentioned. So the magnetic field melts the charge ordering to drive the system into the metallic state. And then also you shed X-ray, and then you have a metal insulator transition. And even the non-linear effect, namely the electric field, can drive the system into the metallic systems, and you have a current-induced switching of the resistivity. And here is a list of transition metal oxides, 3D. And a variety of phenomena occurs: metal insulator transition, magnetic orbital ordering, superconductivity, colossal magnetic resistance, and Malta effect, etc. And then let me mention about the spin-orbit interaction. And then if you go down to the periodic table, so then you increase your spin-orbit interaction, and also you decrease your Coulombic interaction because your orbital becomes more extended, right? So then these 4D materials iridate, so the U is a spin-orbit interaction becomes comparable. So in this situation, then the picture is like that. And effectively, you have the effect 1/2. I already mentioned about the Kita-F interaction by Karim. But in this case, this spin orbit helps to develop the moto-insulating state in the case of strontium iridium oxide. And then this is a wave function for the J1/2 state, etc. But with the remaining a few minutes, let me mention about the non-collinear magnetism. So here is a ferromagnetic state, and this is an anti-ferromagnetic state. The common feature of these two states is that each spin uses only one line, right? For example, the z direction. But if you have a different wave number, then you need to change the magnitude of the spin. And if you have a strong correlation, right? So then this will cost the energy because this moment formation is driven by the Coulombic interaction because the secondary electron cannot occupy the orbital, which is already occupied, right? But then in order to avoid this reduction of spin moment, then the only way is you go to the non-collinear spin structure, right? So then this leads to the variety of phenomena. But I want to mention that this one is related to the classical versus qubit due to the spin degrees of freedom, right? Because this linear combination of 0 and 1, up and down spin, correspond to the spin in the different direction. And in this non-collinear state is related to the multi-Felix. But in this transition metal oxides, so this coupling between the polarization and magnetization is a very, very important key issues. And for example, this is a very representative work by our chairman, Vincent, and using the ferroelectric tunnel junction with ferromagnetic electrons. So then you can enhance the coupling between the polarization of this BTO and magnetization. So this is a strong coupling between the M and P degrees of freedom. And this is a typical multi-Felix where the two symmetries are simultaneously broken. But here is the most important figure I want to show you. Then this is mathematics, right? So this is product of the three vectors. But in the spin-orbit interaction, this ABC corresponds to the ES spin and the velocity of electrons, right? But there are three ways to represent this spin-orbit interaction. So then, depending on the expression, you have a completely different physical picture. For example, in this case, E is coupled to the spin current. So this means your spin current can produce polarization, right? So then the spin degrees of freedom can produce a polarization in the presence of a spin-orbit interaction. Or your E cross S corresponds to the vector potential, which is acting on the velocity. And this E cross S or P cross M corresponds to the so-called toroidal moment defined for the magnetic systems. And also, if you have a V cross E, then this velocity and polarization of the system corresponds to the Zeeman field. So this is so-called Edelstein effect. So all the related spintronics function of spin-orbit system is understood in terms of this formula. Actually, that is my message. And for this one, what is the spin current? And the spin current can be derived in terms of Heisenberg equation motion. And then this S dot T is given by the S cross S. So once you have S cross S, that corresponds to the spin current. So then the spin current leads to the polarization. So that is the machinery for the multi-Felix. Okay, so that one is explicitly driven by this formula, expressed by this formula for the polarization for the coming from the two magnetic ions are expressed in this way. And actually, this one was quite useful to predict the polarization produced by this non-linear spin structures, right? And then this experiment in the dysprosium manganese oxide can be understood in terms of this spiral structure of the magnetic spins, right? So this is one of the basic mechanisms for the multi-Felix. And also, this spin orbit can be controlled or fabricated in terms of interfacial structure. And if you have a cobalt and platinum, so the spin orbit interaction in the platinum will be transferred to the Jarzynski-Moria interaction in the cobalt side, where you have a magnetic moment, right? So then this is a picture for the interfacial magnetic or Jarzynski-Moria interaction. And then this DM interaction as a function of the thickness of this intermediate region. And then let me skip this and skip this because I will talk about this emergent stuff in the next lecture on Saturday. And then probably, okay, lastly, let me mention about the superconductivity. So this is the main TC as a function of years. And then this one is rather suspicious. So the highest temperature up to now is, yeah, actually I talked to my experimental friend about these materials, and he said he doesn't believe the paper. So that's why I put the question mark here, right? So this is a very competitive field, and many reports in the Nature and Science, etc. And then there was some trial to reproduce. But in any case, this is a quite interesting material. And then almost maybe this temperature in the Siberia, right? And then, but you can see this pressure, right? This is almost 200 gigapascal, right? This is a problem. And then this is hydrogen. Because we want to use the high temperature superconductor in the usual ordinary conditions, right? But even though this high pressure is needed, this oxygen superconductor is very promising. But other than that, this magnetic oxide is another promising candidate for the higher TC. And actually, this is a cuprates system. And starting from the D9 configuration of this two-dimensional network of oxygen kappa, and this is a charge transfer insulator. And if you introduce holes, then you have a Zanlai singlet, can be described by the so-called TJ Hamiltonian in terms of two-dimensional. Okay, and then I want to mention that in 90s, maybe some of you are still not exist, right? Yeah, once you are 25, etc., then you are not. But in that case, we have 4 conditions, right, for high TC superconductor: strong correlation and singlet over spin 1/2. The fluctuating spin is essential, and then single orbital. So because cuprates, you have only the x square minus y square orbitals. So then single orbital is essential, because at that time nickelate didn't show the superconductivity. Right? So that was reasoning, and you need 2D materials. So these are the list of conditions for high TC. But now people are becoming suspicious about this, right? One reason is nickelate, right? So nickelate, you have still the orbital degrees of freedom, right? Let's say x square minus y square and 3g square, right? So the coexistence of the two might be important for this nickelate. But in this case, this original report by Harold himself in 2019, and this is materials, right? So this is an iodium nickelate oxide. So this is valency, and then this strontium gives to the whole doping. So this is rather similar to the cuprate case, where you are starting from D9 and introduce a hole. So that was his original motivation to look for the analogy of high TC cuprates in the nickelate. But now this is also a very, very, very important and exciting field, and people are becoming more and more conscious about the orbital degrees of freedom of the nickelates. Okay, so that's all what I want to say, and I couldn't talk about emergent electromagnetism, but please come to my lecture on Saturday on this emergent electromagnetism. Thank you very much for your attention.